Isn't it wild how some books just, take off? Like Stephen Hawking's A Brief History of
Oh,
Time.
absolutely, a phenomenon.
Totally. It was on the London Sunday Times bestseller list for, get this, 237 weeks.
That's staggering. Longer than almost anything
Or
else,
pretty
right?
much. Maybe
Yeah.
even beating the Bible or Shakespeare, depending how you count it. And Hawking himself pointed out he sold more copies about, like, physics than Madonna did about sex.
He really said that. That's
Yeah.
brilliant.
It just, it makes you think, doesn't it? What are people actually curious about?
It really does. That fundamental urge, to understand our place in it all.
Exactly. And that's what we're doing today. Just for you, the learner, we've got insights mainly from Hawking, but also drawing on Ron Miller, Carl Sagan, that kind of vibe.
Right. Deep dive.
Our mission, to unpack the big ideas, how we picture the universe, how that picture changed, ancient models, modern
All
physics,
the way to the shape of the universe, time itself.
and that huge quest, right? The unified theory. We're aiming for those aha moments, hopefully without the technical overload.
Okay, let's dive in. It's easy to forget just how different our view used to be.
Right. Hawking starts with that great story. Scientist gives a talk on astronomy. Earth orbits the sun orbits the galaxy.
Mm-hmm.
And this old lady stands up, says it's all rubbish. The world's a flat plate on a giant tortoise.
Classic. And when the scientist asks what the tortoise is standing on,
She just smiles. It's turtles all the way down.
huh. It's funny, but it really shows that massive gap, doesn't it, between sort of intuitive myths and actual scientific models based on evidence.
That's a key takeaway right there.
And think about how long some of those old models lasted, like the Ptolemaic system.
Earth at the center, everything else on spheres,
Yeah.
epicycles.
Exactly. And it held sway for centuries. It was the explanation.
And the church really liked it, didn't they? Hawking mentions that. It left room outside the stars for,
Heaven and hell?
precisely, fit the worldview. Very
Yeah.
convenient theologically. But even then, there were cracks, weren't there? Things that didn't quite fit the observations.
Yeah, like the moon. Ptolemy's model had it sometimes looking, well, twice as big as other times, which he clearly doesn't.
He knew about that.
He did, apparently. But the model stuck anyway. Inertia, I guess.
Until Copernicus comes along, 1514, puts the sun in the middle, Earth moves.
A huge shift. And he was careful, right?
Yeah.
Circulated it anonymously at first.
Yeah, probably worried about being called a heretic. Understandable. Took ages to catch on.
Well, it wasn't just science, was it? It was challenging humanity's whole place in the cosmos, taking us off the pedestal.
That makes total sense. But the evidence just kept building.
Ah,
Kepler.
Kepler. He fixed Copernicus's circles, realized the orbits were elliptical,
And that finally made the predictions match what astronomers were actually seeing.
and then Galileo turns his telescope to the sky. 1609.
And sees moons orbiting Jupiter.
Exactly. Direct proof that not everything goes around the Earth.
Hawking says you could still try to make an Earth-centered model work, but it got ridiculously complicated. Copernicus's idea was just simpler, more elegant.
So observation plus better math. Step by step, it changed everything. A gradual revolution.
Okay, so that's the history. Let's jump to now the big leagues. The two pillars of modern physics.
Right? General relativity and quantum mechanics.
Two incredibly successful theories. Einstein's relativity for gravity, the big stuff, planets, stars, galaxies.
A whole universe, basically. And then quantum mechanics for the tiny stuff. Atoms, particles,
Little weird stuff.
the very weird stuff, yeah. And here's the rub. They work brilliantly in their own domains.
But they just don't play nicely together, do they?
Not at all. When you get situations with really strong gravity, on really small scales, like inside a black hole or right at the Big Bang,
They break down or contradict each other.
pretty much,
Yeah.
they give nonsensical answers like infinities. It shows we're missing something.
And finding that missing piece, Hawking says that's the huge challenge, a quantum theory of gravity.
The Holy Grail, really.
Yeah.
A single theory for everything.
Tying back to that deep human need to just understand it all.
Exactly. Imagine finding that. It would be monumental.
Okay, let's dig into those pillars, starting with relativity and how it completely messed with our ideas of space and time.
Before Einstein, you had Newton building on Aristotle, this idea of absolute rest.
Things stay still unless you push them, and Earth was considered like the ultimate still thing.
But Newton's own laws kind of undermine that, didn't they? Hawking's train analogy is great here.
The ping pong ball.
Yeah. Bounce it on a smoothly moving train. To you on the train, it goes straight up and down.
But to someone outside, it's moving forward too, tracing an arc.
So, which path is real? There's no absolute answer, no absolute rest.
And if there's no absolute rest, there's no absolute position either, right? The two bounces happen in the same spot on the train, but different spots relative to the ground.
Exactly. Space wasn't absolute, but everyone, Aristotle, Newton, they still clung to absolute time.
Like a giant cosmic clock ticking the same for everyone, everywhere. Seems intuitive.
It does. But that's where Einstein really shook things up, especially when things move very, very fast.
Near the speed of light.
Right. And the key experiment, way back in 1887, was Michelson-Morley.
They were looking for the ether, weren't they? This invisible stuff light was supposed to travel through.
Yeah, they expected Earth's motion through the ether to affect the measured speed of light.
But they found nothing. The speed was the same no matter which way the Earth was moving.
A huge surprise, a null result that couldn't be ignored.
Baffling. People like Lorentz tried to patch it up, didn't they? Objects shrinking, clocks slowing in the ether.
Trying to save the old idea. But Einstein, 1905, just cut through it. He said, forget the ether. What if the speed of light is always constant for everyone?
And the thing that has to give way is our idea of absolute time.
Precisely. Poincaré had similar math, but Einstein grounded it in the physics, in the measurements.
And the consequences are just mind-bending. If everyone agrees on light speed,
then they have to disagree on distances and time intervals between events if they're moving relative to each other.
so my now isn't necessarily your now if we're moving differently.
Exactly. No universal clock. Everyone has their own personal time. It even depends on gravity.
The twins paradox. One travels fast, comes back younger.
Or even just living on a mountain versus sea level. The twin on the mountain ages infinitesimally faster. It's measurable.
Wow. So space and time aren't separate things at all.
They're interwoven, a four-dimensional fabric.
Yeah.
Space-time. 3 space dimensions, 1 time dimension.
Hard to visualize 4 dimensions, though.
Oh, definitely. Hawking admits struggling with 3 sometimes. But we use analogies like the 2D surfaces of the Earth, or those space-time diagrams, time going up, space across.
And within space-time, you have light cones.
Right. For any event, there's a future light cone everywhere you can reach going at or below light speed, and a past light cone everywhere that could have reached you.
And anything outside those cones is elsewhere.
Elsewhere. Can't affect you, you can't affect it. Because nothing travels faster than light. Causal separation.
That's why we see distant stars as they were, not as they are now.
Exactly. If the sun vanished now, we wouldn't know for 8 minutes. Where it's elsewhere until the light, or lack thereof, reaches us. We're always looking into the past when we look out.
Okay, so that's special relativity. Space, time, light speed. But where's gravity in all this?
That took Einstein another 10 years. General Relativity, 1915. His masterpiece.
And it's not a force pulling things.
Not in the Newtonian sense. Einstein said, gravity is the curvature of space-time caused by mass and energy.
Like a bowling ball in the rubber sheet analogy?
Perfect analogy. The ball makes a dip, and marbles rolling nearby curve towards it because they're following the curve of the sheet, not because the ball is pulling them directly.
So planets orbit the sun because they're following the curves in space-time caused by the sun's mass.
Exactly. They're following the straightest possible paths, geodesics, through curved space-time.
And light does too, even though it has no mass.
Light follows geodesics too, so gravity bends light. General relativity predicted light from distant stars would be deflected as it passed near the sun.
And they tested that during the 1919 eclipse.
They did. Saw the stars' positions shift, just as Einstein predicted, made him world famous overnight.
Though Hawking adds a little caveat, right, that the initial measurements were maybe a bit shaky.
A little bit, yeah. The effect was tiny, errors were large, maybe some wishful thinking, but it's been confirmed much more precisely since then. It's real.
So gravity is geometry, the shape of space-time itself. Wow. Okay, how do we get from bending starlight to the whole universe expanding?
Well, fast forward to the 1920s. Astronomers like Hubble start looking closely at the light from other galaxies.
And they see the redshift.
You see the redshift. The spectral lines, the fingerprints of elements were all shifted towards the red end of the spectrum.
Which means they're moving away from us. Like the Doppler effect with sound, but for light. Lower pitch means moving away. Redder light means moving away.
Exactly. And the crucial discovery was, the farther away the galaxy, the bigger the redshift.
Meaning the faster it's moving away.
Right. The whole universe seemed to be expanding, everything moving away from everything else.
And if you run that movie backward,
everything comes together, back to a single point, an incredibly hot, incredibly dense state.
the Big Bang.
The Big Bang. But it wasn't the only game in town initially. There was the steady state theory.
Bondi, gold, Hoyle, 1948, what was their idea?
They proposed that as the universe expanded, new matter was continuously created in the gaps.
So the universe would look basically the same, on average, at all times. No beginning.
Exactly. An eternal, unchanging universe just expanding.
But the evidence started piling up against it, didn't it? Radio source counts.
Right. Surveys in the 50s and 60s found more radio sources far away, meaning earlier in time than nearby. That didn't fit steady state.
And then the killer blow. The cosmic microwave background.
The CMB, Penzias and Wilson, 1965. Trying to calibrate a microwave antenna, they find this faint background hiss.
Shining from everywhere in the sky. Couldn't get rid of it.
Couldn't get rid of it. Turned out to be the leftover heat, the afterglow, from the hot Big Bang itself.
Exactly what Gamow and others had predicted decades earlier. They were even building detectors to look for it.
Incredible discovery. Huge confirmation for the Big Bang. It painted a picture of a universe that started incredibly hot and dense, then cooled as it expanded.
And that cooling allowed things to form, like atomic nuclei.
Precisely. In the first few minutes, it was cool enough for protons and neutrons to fuse into deuterium and helium. The amount of helium predicted by Big Bang calculations matches what we observe perfectly, another huge piece of evidence.
So steady state was pretty much out, Big Bang was in, but what about that very first moment, the singularity?
Yeah, the math of general relativity, these Friedman models describing the expansion, they all point back to a time zero.
Where distances are zero, density is infinite.
Infinite density, infinite space-time curvature, a singularity, a point where the laws of physics, as described by general relativity, just break down.
So the theory predicts its own failure at the very beginning.
In a sense, yes. It tells us we can't use it to describe what happened at time zero or before, if before it even makes sense. Science kind of starts just after the singularity.
Which made some people uneasy. Seemed like it needed a creator.
Some thought so. Hawking notes the Catholic Church was actually quite comfortable with the Big Bang model initially.
Interesting. And Penrose and Hawking himself proved mathematically that based on general relativity, our universe must have started from a singularity.
They did, in 1970. Powerful work. But ironically, Penrose's work also showed singularities form inside black holes. And Hawking later came to think that maybe, just maybe, if you add quantum effects, the initial singularity at the start of the universe might disappear.
Which brings us neatly to quantum mechanics, the other pillar. The physics of the very small.
And it's a completely different beast from general relativity's smooth space-time. It's inherently uncertain, probabilistic.
Heisenberg's uncertainty principle can't know position and momentum precisely at the same time.
That's a core part of it. And the weird wave-particle duality, things can act like waves and particles.
Like light. It makes interference patterns like waves and soap bubbles.
But it also comes in packets, quanta, photons. Max Planck figured that out.
And electrons do it too, the double slit experiment.
The classic. Fire electrons one by one through two slits, and they still build up an interference pattern on the screen, as if each electron somehow went through both slits like a wave. Bizarre.
Mind-bending. How did this help with atoms? The old model had electrons spiraling into the nucleus, right?
Yeah, classical physics said atoms should collapse instantly. Bohr's model was a breakthrough. He just postulated electrons could only exist in specific orbits, specific energy levels, quantized orbits.
It worked. Explain atom stability, the light spectra they emit.
It worked remarkably well as a first step, but the full theory of quantum mechanics developed later provided a much more complete picture.
But still, that fundamental clash remains. General relativity for the big, quantum mechanics for the small.
And they don't mesh, especially where you need both strong gravity, small scales, black holes, the Big Bang.
General relativity predicts singularities, points where it breaks down.
Almost signaling you need quantum mechanics here. It points towards the need for a quantum theory of gravity.
The big quest. Okay, before we get to that quest, let's talk building blocks. Fundamental particles, fundamental forces.
Right. We know atoms aren't fundamental. Protons, neutrons aren't either. They're made of quarks. So what is truly elementary?
Depends how hard you look, like how much energy you use to probe.
Exactly. Higher energy accelerators are like more powerful microscopes. They reveal smaller structures.
And what have we found so far? What are the categories?
Broadly, two types. Matter particles, they have half-integer spin, like spin on half-half. Think quarks, electrons. They obey the Pauli exclusion principle.
Which says no two identical matter particles can be in the exact same state at the same place and time.
Right. Crucial for stability. It's why matter takes up space, why everything doesn't collapse.
And the other type?
Force-carrying particles. They have integer spin, 0, 1, 2, like photons. They don't obey the exclusion principle. Lots can pile into the same state.
And forces arise from exchanging these particles.
That's the quantum picture. Matter particles interact by tossing these force-carrying particles back and forth. Virtual particles often. Can't see them directly in the exchange, but you see their effect.
Okay, the four fundamental forces we know are
Gravity, mediated by the hypothetical graviton. Electromagnetism, the photon. The strong nuclear force, holding atomic nuclei together, gluons. And the weak nuclear force, responsible for radioactive decay, WZ bosons.
and we've managed to unify some of these.
Big success story there. Weinberg and Salam, late 60s, showed electromagnetism and the weak force are actually two aspects of a single electroweak force and high energies.
They look different at low energies because of spontaneous symmetry breaking.
Exactly. Hawking's roulette wheel analogy.
Mm-hmm.
High energy, the ball rolls anywhere. Symmetry.
Crap.
Low energy, it falls into one specific slot. Broken symmetry.
Brilliant. And people then tried to unify the strong force, too, GUTs.
Grand Unified Series, yeah. Aiming to combine the strong and electroweak forces at even higher energies. Some GUTs even unify quarks and leptons.
But they don't include gravity.
Not yet. That's the big missing piece. And GUTs still have parameters you have to plug in from experiments. Not fully predictive, but a step in the right direction.
And all this relates to fundamental symmetries in nature, CPT.
Right. Charge, parity, mirror image, time reversal. It used to be thought all laws obeyed these separately.
Until the 50s. Li and Yang suggested the weak force violates parity.
They did, and Wu's experiment confirmed it. Huge shock. The universe isn't perfectly mirror symmetric at the fundamental level.
And it violates C, too, charge symmetry.
The weak force does, yes. For a while, they thought the combined symmetry, CP, held.
But then Cronin and Fitch found even that is violated sometimes in Camus and Decays.
Exactly, 1964. So the universe has these subtle, built-in asymmetries.
But the combination CPT charge, parity, and time reversal altogether, that seems to hold?
So far, yes. CPT symmetry looks fundamental, which has a massive implication.
If CP is violated, but CPT holds.
Then T, time reversal symmetry, must also be violated on its own. The laws of physics aren't perfectly time reversibles as we experience them, tied to the arrow of time.
Wow. Okay, deep stuff. Let's switch gears to something predicted by relativity, but equally weird. Black holes.
The ultimate gravitational collapse. Need to think about how stars live and die first.
Stars form from collapsing gas clouds, heat up, ignite nuclear fusion.
Right. Hydrogen fuses to helium, releases energy. That outward pressure balances gravity's inward pull. Star is stable for billions of years.
Until it runs out of fuel.
Then gravity takes over. What happens next depends on the star's mass.
Smaller stars become white dwarfs, supported by electron pressure. Pauli principle, again.
Yep, more massive ones collapse further. Electrons forced into protons become neutron stars, supported by neutron pressure. Incredibly dense.
But if the star is really massive, above a certain limit...
The Tolman-Oppenheimer-Volkoff limit.
Yeah.
Then even neutron pressure can't stop gravity. Collapse continues indefinitely, forms a black hole.
A region where gravity is so strong, nothing escapes. Not even light.
That's it. Once you cross the boundary, the event horizon, you're trapped.
What's it like for someone falling in, say, an astronaut?
For someone watching from far away, the astronaut seems to slow down approaching the horizon, gets redder and dimmer.
And seems to freeze there forever, fading out.
Exactly. Time dilation and redshift become infinite at the horizon from the outside view.
But for the astronaut themselves.
They might not notice anything special right at the horizon, especially for a big black hole. But as they get closer to the center, tidal forces,
Spaghettification.
lovely term, yes, stretched head to toe, squeezed side to side by the extreme gravity gradient. For smaller black holes, this happens before the horizon.
And at the very center, general relativity predicts a singularity.
Infinite density, infinite curvature, the end of space and time as we know it, physics breaks down.
But we can't see it from outside. The horizon hides it.
Seems so. Penrose's cosmic censorship hypothesis. Basically, nature avoids naked singularities, always cloaked by an event horizon.
And black holes are simple, right? Just mass and spin, maybe charge.
Classically, yes. All the complexity of the star that formed it gets lost. Just those few numbers describe it.
Was there pushback initially? Did scientists believe they were real?
A lot of skepticism. Seemed like mathematical artifacts. But then came evidence. Martin Schmidt, 1963. Quasar 3C273.
Huge redshift, incredibly distant, incredibly bright.
Had to be powered by something immense. Best explanation. Matter falling into a supermassive black hole at the center of a galaxy.
And now we have pictures, right? Like M87, seeing the shadow of the event horizon.
Incredible stuff. Seeing rotating gas disks, jets being launched, strong evidence for these monsters, billions of solar masses at galactic centers, they power quasars.
And there might be tiny ones too, primordial black holes.
Possibly. Formed in the dense early universe, detecting them would tell us a lot about that era.
Okay, so black holes trap everything except Hawking's biggest discovery. They aren't completely black.
Hang on, what? That sounds like a contradiction.
Classically, it is. But bring in quantum mechanics near the event horizon. Things get weird. Hawking's insight in the 70s. Quantum fluctuations, virtual particles popping in and out of existence.
Exactly. Particle-antiparticle pairs, borrowing energy from the vacuum for a tiny moment, then annihilating. Happens everywhere.
But near an event horizon,
One particle can fall in, the other can escape. If the one falling in has negative energy relative to the outside.
it reduces the black hole's mass, and the escaping one looks like radiation from the black hole.
Precisely. That's Hawking radiation. The black hole effectively emits particles, glows with a thermal spectrum, it has a temperature.
Black holes have a temperature. Wow.
And here's the kicker. Smaller black holes are hotter. They radiate more intensely.
Counterintuitive, so they lose mass
Ruh.
and eventually evaporate completely.
Over unimaginably long timescales for stellar mass ones, yes, but they do evaporate, which
Yep.
might mean the singularity inside eventually disappears too. Quantum effects resolving the classical problem, perhaps.
Mind blown. Okay, let's zoom back out. Universe as a whole. The hot Big Bang model.
The standard picture. Universe starts hot and dense, expands and cools.
And that cooling dictates what happens when, like, phases changing.
In the first fraction of a second, just a soup of fundamental particles and antiparticles, photons, neutrinos.
Then it cools, matter-antimatter annihilates, leaves a slight excess of matter.
Right. Then, after a few minutes, cool enough for protons and neutrons to fuse nucleosynthesis, making deuterium, helium.
Again, the predicted helium amount matches observations perfectly.
Bang on. Strong evidence. Gamma, alpha, Bath figured this out. They also predicted...
Leftover radiation, the CMB.
Exactly. Predicted it would still be around, cooled down to microwave temperatures. Penzias and Wilson found it.
So the model hangs together really well. Then over billions of years, gravity works on tiny initial irregularity.
Amplifying them, pulling matter together to form galaxies, stars, planets, eventually us.
But general relativity still hits that wall at time zero, the singularity.
It does. Which leads to philosophical questions.
Yeah.
Like the anthropic principle.
The weak version sounds almost obvious, doesn't it? We see the universe the way it is because if it were different, we wouldn't be here to see it.
It's a selection effect, basically. Our existence restricts the type of universe we can observe.
But the strong version is weirder, that the universe must have properties allowing life.
Yeah, that's more controversial. Some take it to mean multiple universes exist, with different laws or constants, and we just happen to be in a life-friendly one.
Like a cosmic lottery winner?
Kind of. But Hawking and others are skeptical. If other universes are unobservable, are they really science? Occam's razor.
And it feels a bit backward, putting us back at the center almost, after centuries of science doing the opposite.
That common objection, it feels like giving up on finding a physical explanation for why our universe has the properties it does.
Which leads to ideas like inflation.
Right. Alan Guth, early 80s, proposed the universe went through a phase of incredibly rapid exponential expansion very early on, like fractions of a second after the Big Bang.
Why? What problems does that solve?
It helps explain why the universe looks so uniform on large scales, and why it's so geometrically flat. Inflation would stretch out any initial wrinkles, smooth everything out.
How would it work? Like a phase transition, water freezing?
Sort of.
Yeah.
As the universe cooled, maybe it got stuck in a high-energy, false vacuum state, which drove this rapid expansion, this sort of repulsive gravity. Then it transitioned to the lower energy state we're in now, releasing energy, reheating the universe into the hot Big Bang state.
Guth's original model had issues, bubbles not merging.
It did. But newer versions, like chaotic inflation, seem to work better mathematically. And the beauty is, inflation could potentially take a wide range of messy initial conditions and still produce a universe like ours. It reduces the need for extreme fine-tuning at the start.
Though Hawking cautions it doesn't solve everything, right? A really lumpy start might still end up lumpy.
True. It doesn't mean any start works. The question of the ultimate initial state still lingers.
And to tackle that, we need quantum gravity, which brings us back to Feynman's sum over histories.
A really powerful idea from quantum mechanics. To find the probability of a particle going from A to B, You don't just look at one path. You sum up contributions from all possible paths it could take.
Even crazy zigzagging paths.
Even those. Each path has a probability amplitude. You add them all up.
And Hawking and Hartle applied this to the whole universe.
Bold move.
Right.
Sum over all possible histories, all possible curved spacetimes the universe could have.
How do you even do that calculation?
It's incredibly complex. One trick is to use imaginary time. Treat the time coordinate mathematically like another space dimension.
Imaginary time, is that real?
Not physically real like space. It's a mathematical tool that turns the equations into something more like statistical mechanics, easier to handle. It helps smooth things out.
And this leads to the no boundary condition.
The Hartle-Hawking state. The idea is, in this imaginary time picture, the universe is finite, but has no boundary, no edge, no beginning or endpoint, like the surface of a sphere.
Finite area, but no edge you can fall off.
Exactly. If the universe has no boundary in imaginary time, then there's no singularity in real time where physics breaks down. No need to specify initial conditions at a boundary because there isn't one.
The universe just self-contained.
That's the profound implication. No creation event needed, no initial singularity to explain away.
Does this make testable predictions?
It predicts the universe should have started very smooth and ordered, with just the minimum quantum fluctuations allowed by the uncertainty principle.
And inflation would then stretch those tiny fluctuations,
Making them the seeds for galaxies and large-scale structure. And the Kobe satellite measurements of the CMB variations seem to fit this picture really well.
So it's a potential way to have an ordered beginning without needing to fine-tune it.
Exactly. It offers a potentially elegant solution to the initial conditions problem.
Okay, let's loop back to time, the arrow of time. Why does it only go one way for us?
Our subjective experience is undeniable, right?
Yeah.
Past behind, future ahead. Memory works one way. But the basic laws of physics?
Mostly don't care. They work forwards and backwards. CPT symmetry.
Largely, yes. At the micro level, most interactions are time reversible. Billiard balls colliding looks fine in reverse.
But a broken cup reassembling itself, that looks wrong. Impossible.
That's the second law of thermodynamics kicking in. Entropy, disorder. Systems tend to go from ordered states, whole cup, to disordered states, broken pieces.
Disorder increases over time. That's the thermodynamic arrow.
Right, and Hawking argues our psychological arrow, how we remember things, is tied directly to that thermodynamic arrow.
Our brains record things in the order that entropy increases.
Essentially, yes. Processing information, forming memories, it all increases the overall disorder of the universe. It's easier to remember the disordered state, broken cup, than the highly improbable ordered one, cup spontaneously forming.
Okay, but why is there a thermodynamic arrow at all? Why did the universe start so ordered in the first place?
That's the key question. If it started randomly, it should have started disordered. The no boundary proposal offers an answer here too.
It predicts a smooth, ordered start in imaginary time.
Which translates to a smooth, ordered start in real time, giving entropy room to increase, creating the thermodynamic arrow.
And why do the thermodynamic arrow, increasing disorder, and the cosmological arrow, universe expanding, point the same way?
Here, Hawking uses the weak anthropic principle again. He argues intelligent life needs a strong thermodynamic arrow to function. We need order to turn into disorder to live and think.
And maybe those conditions only exist during the expanding phase.
That's his suggestion. A contracting universe might be heading towards order, reversing the thermodynamic arrow, making memory work backwards. But maybe complex life just couldn't survive or evolve in that kind of environment anyway.
So we only find ourselves observing the universe during its expanding phase when the arrows align in a way that allows us to exist.
It's a plausible anthropic argument, connecting the arrows through our own existence.
Okay, from the fundamental nature of time to science fiction, wormholes, time travel.
Always fascinating. H.G. Wells got us started.
Yeah.
But could it be real?
Gödel found solutions in general relativity that allowed it. Closed time-like curves.
He did, mathematically. A rotating universe solution where you could loop back into your own past. But is that our universe? Probably not.
And even getting between stars is hard enough, right? The distances are insane.
Alpha Centauri, 4 light years. Galactic center, tens of thousands. Even light takes ages.
Time dilation helps the traveler, but not the people back home.
Right. You might make a long trip in your lifetime, but centuries could pass on Earth.
And faster than light travel seems linked to backwards time travel. The limerick.
Yeah, arrived on the previous night. Yeah. Relativity implies FTL equals time travel relative to some observers. Seems forbidden.
What about wormholes? Einstein-Rosen bridges, shortcuts through space-time.
Theoretically possible in GR, but the simple versions collapse instantly. Useless for travel.
Could you prop one open? What would that take?
According to theory, you'd likely need exotic matter, stuff with negative energy density, to create the negative curvature needed to hold the wormhole throat open or warp space-time for time travel.
Negative energy density, does that even exist?
Classically, no, but quantum mechanics allows it. The Casimir effect is experimental proof. Tiny regions between metal plates can have negative energy density relative to the outside vacuum.
So maybe it's not completely impossible? Theoretically?
Theoretically, maybe not completely, but the engineering challenges would be astronomical, to say the least. And then there's the paradox problem.
Right. If time travel is possible, where are the tourists from the future?
Good question. Maybe it's forbidden. Maybe the past is fixed. Maybe they can only travel into their future. Hawking favored the idea that the past is fixed because we've observed it.
And the grandfather paradox. Go back, kill grandpa, prevent your own birth.
How do you resolve that? Two main ideas. Consistent histories.
Meaning you just can't change the past in a way that creates a paradox. You were always part of that history. No free will in the past.
That's one view. The universe enforces self-consistency.
Or alternative histories, branching timelines.
The multiverse idea. Changing the past creates a new parallel universe. You don't change your past.
Which does Feynman's sum over history support?
Hawking felt it leaned more towards consistent histories, summing over complete, self-consistent spacetimes.
And he proposed the chronology protection conjecture.
Basically, a hunch that the laws of physics themselves prevent macroscopic time travel, protecting causality, like cosmic censorship for singularities. Not proven, but plausible. Which brings us, finally, to the ultimate goal, unification. A theory of everything.
Bringing general relativity and quantum mechanics together, the big dream.
Einstein chased it for decades, but failed. Didn't accept quantum mechanics fully, didn't know about the nuclear forces as well as we do now.
The big problem is combining them naively gives infinities, like infinite energy in empty space.
Exactly. Virtual particles bubbling everywhere, their combined energy should curve space-time into a tiny ball, according to relativity. But it doesn't. Something's wrong with the simple combination.
Early attempts like supergravity didn't quite work.
Showed promise, introduced symmetry between matter and force particles, but ultimately hit dead ends. Then came string theory.
The idea that fundamental particles aren't points, but tiny vibrating strings.
One-dimensional strings, open or closed loops. Different vibrations correspond to different particles, electron, quark, photon, even the graviton. Interactions are strings joining and splitting.
Elegant picture. Where did it come from?
Started as a theory for the strong nuclear force, oddly enough. Then they realized if the string tension was much higher, it naturally included a quantum description of gravity.
But it needs extra dimensions, like 10 or 11.
Mathematically, yes, to be consistent. These extra dimensions are supposedly curled up, compactified, incredibly small, so we don't see them.
Like the surface of a straw looking 1D from far away, but having a curled up 2D surface up close.
Good analogy. Why three large space dimensions? Maybe the anthropic principle again. Maybe that's what's needed for complexity, for life.
But there were multiple string theories, and lots of ways to curl up the extra dimensions. Seemed messy.
It did. But then came the duality revolution in the 90s. Physicists found these different theories were actually just different mathematical descriptions of the same underlying thing.
Different perspectives on one deeper theory.
Exactly. And it wasn't just strings, but higher dimensional objects called p-branes too, all hinting at a single overarching framework.
M theory.
M theory. Still mysterious, not fully formulated, but it seems to unify the different string theories, supergravity, p-branes, our best candidate for a theory of everything right now.
And how does the no-boundary proposal fit into this quest?
It offers a way to handle the beginning. If the universe is self-contained, no boundary, no singularity, then the unified laws should apply everywhere, right from the start in imaginary time.
It constrains the initial state, removes the need for arbitrary choices.
Potentially. Revisiting Einstein's question, how much choice did God have? If the no-boundary idea is right, maybe very little choice in the initial conditions. Maybe the only choice was in picking the fundamental laws themselves, laws consistent enough to allow complexity in life to emerge.
Wow. Finally, Hawking ends by tipping his hat to the giants, right? Galileo and Newton.
Absolutely. Galileo, championing observation, experiment, challenging authority, really the birth of modern science.
Facing down the church over the Copernican view, insisting we can understand how the world works.
And Newton. Difficult man, apparently. Lots of disputes, Flamsteed, Leibniz over calculus.
But his Principia, just monumental, laid the foundation for classical physics for centuries. Gravity, motion.
These two really set the stage, moved us from dogma to observation, math, testable theories, that whole scientific journey we're still on.
So there you have it, the learner. What a ride, from turtles all the way down.
To curved space-time, quantum weirdness, black holes evaporating, extra dimensions.
And the ongoing hunt for that ultimate unified theory. We hope this deep dive, especially into Hawking, gave you a shortcut to wrapping your head around some seriously big ideas.
Without getting totally lost in the cosmic sauce.
Yeah, and maybe the most amazing thing isn't any specific law we found.
But just the fact that the universe seems to follow rules. Rules we can actually figure out, even if they're baffling sometimes.
Exactly. That we can even do this science makes you wonder, what else is out there? What secrets are just over the horizon?
Something to ponder. What comes next?
Definitely something to think about. Thanks for joining us on this deep dive.